It is important to consider that much of what is discussed here are reasoned hypotheses that may or may not be confirmed. Indeed, all of science is built upon this foundation. There is a notion that certain topics, when contemplated deeply enough, can quite literally drive a person to madness. Perhaps you've sensed this when exploring similar ideas, assuming, of course, a certain level of impressionability. It is possible that today we will delve into the abyss of potential madness more profoundly than ever before. Many have heard that the age of our universe is approximately 13,800,000,000 years, and that it originated from a Big Bang. But the question here is what we call the universe and what beginning signifies. When you hear the phrase, the universe appeared from nothing, it likely means not from absolute nothingness, but from something we do not yet know how to describe. Furthermore, theoretical physicist Matt Strassler, in his article, The Hot Big Bang, writes that, when we speak of the age of the universe, we are only referring to the period from the beginning of the Big Bang to the present day, but this does not mean that nothing existed before the Big Bang, and a similar principle applies not only to time, but also to space itself. It is suggested that the universe was concentrated into an infinitely small point at the moment of the Big Bang and supposedly had a finite size, perhaps smaller than a single atom, or so it is often said in popular science. However, this refers only to the observable part of the universe. Thus, it does not at all mean that the universe was not infinite at the moment of the Big Bang. In fact, all data suggests that the universe is indeed infinite, which means it was much denser but still just as infinite at its very beginning. And infinity is one of those things you probably shouldn't think about too much. Soon, everything said will become a little clearer. In August of 1881, Nietzsche was strolling along Lake Silvaplana, near the village of Sils Maria in Switzerland, and stopped to rest right by a particular pyramidal rock. At that very moment, the philosopher was struck by an insight so powerful it nearly crushed him, as he would later express in a letter to his friend and assistant Peter Gast. "On my horizon has risen a thought, the like of which I have never known." This moment was so significant that it was immortalized with a plaque on the rock, the quote on which literally states, "I stopped by a mighty pyramidal block not far from Surlade. It was then that this thought came to me." Nietzsche realized that the idea that had struck him should become the most central in his philosophical teaching, but at the same time the most terrible. So terrible that he spoke of it with great reluctance. Many who knew him well, particularly his friend Franz Overbeck and his unrequited love Lou Salome, later reported that Nietzsche spoke of this idea in a whisper, implying it was some unheard-of discovery. According to Nietzsche, this thought would not be crushing, given proper reflection, only and exclusively for the so-called Übermensch or Overman. The Overman is not some comic book character, but an image introduced by Friedrich Nietzsche to denote a being who, by its power, should surpass modern man to the same extent that the latter has surpassed the ape. And speaking of power, it refers more to psychological qualities. We will get to the very thought that illuminated Nietzsche, but first, much needs to be explained. Let's start with one of the most astounding cosmological oddities known. You are aware, are you not, that the farther an object is from us, the smaller it appears? For example, from a bird's eye view, people look like ants. The same occurs in the nearer parts of cosmos. The sun is 400 times larger than the moon, but during a total solar eclipse, the moon almost perfectly covers it because it is 400 times closer to us than our star. And this entire pattern of changing sizes depending on distance persists over billions of light years. That is, the farther a galaxy, the smaller it appears to us, as one would expect. However, at a certain point, at a distance of approximately 14 billion light years, an entirely opposite pattern suddenly begins to operate. Namely, the farther an object, the larger it seems. And there's a simple, yet profoundly somber explanation for this. To begin with, though it is hard to believe, by looking at any star or galaxy in the night sky, you are at that very moment experiencing the gravitational influence of that object. Even if this object is immensely distant, if you can see it, its gravitational field reaches you because gravity propagates at the speed of light. You not only see the sun as it was 8 minutes and 20 seconds ago, but our entire planet is also attracted not to where the sun is now, but to where it was those same 8 minutes and 20 seconds ago. The peculiarity of gravity is that although it weakens with distance, it never reaches zero. It is uncertain if the gravitational influence of very distant objects can be registered at all unless it is, for example, the merger of two black holes. Because gravity as a force is so weak that, metaphorically speaking, one could overcome the gravity of our entire planet with a simple gesture. However, believe it, the force of gravity would be sufficient for all massive objects in our universe to eventually collapse. You could never move far enough from an object to not experience its gravitational influence at some level. Meanwhile, our universe is not collapsing. In fact, something quite the opposite is happening. We do not know why, but the universe is expanding, and it is doing so with acceleration. and since physicists have no idea what causes the universe to expand, they usually call any hypothetical phenomenon capable of accelerating the universe's expansion dark energy. Yes, I know you are probably tired of hearing about dark energy in every other discussion about space, but friends, dark energy is, by all appearances, one of the most repugnant phenomena that exist, so do not dismiss it prematurely. Catherine Mack, an assistant professor of physics at North Carolina State University, writes, "If you ask my colleagues, they will say they strive to understand the nature of dark energy, because it can tell us a lot about fundamental physics and our cosmological model. But I know that what actually drives them is fear." So, the expansion of the universe, rewinding time by 13.8 billion years to somewhere near the very, very conventional beginning, we find a paradoxical moment in which, for reasons not entirely clear to us, the expansion of the universe suddenly accelerated, and the region that was to become our observable universe increased in size by more than 100 trillion times. This happened much faster than the speed of light, because there are no restrictions on the speed of expansion of space itself. I understand that our brains are not equipped to imagine such numbers, but for some clarity, here is what theoretical physicist Matt Strassler, mentioned earlier, writes. How insane were the rates of expansion? A section of the universe no larger than your computer screen expanded to the size of the observable universe, or larger in less time than it takes a quark to cross from one side of a proton to the other. But then this monstrous expansion, again for unknown reasons, slowed down, and this past frenzy is called the cosmic inflation hypothesis. We do not know for sure if that initial expansion is related to the expansion we observe now, but importantly, we currently have no reason to believe that cosmic inflation cannot happen again. For instance, right now, as you consider this, we wouldn't even have time to understand anything. If such a thing were to happen, it would be terrible. Yet the simple disappearance of humanity would not be the worst possible outcome. You might ask, what could be worse for humanity than the demise of all humanity? So, we continue. The universe experienced a stage of inflation after which expansion slowed, but about 6 billion years ago, expansion began to accelerate again. We know this thanks to the processing of vast amounts of data, including by complex modern computer programs. You have surely heard that the universe expands not from a specific point, but at all points simultaneously, and therefore, the farther an object is, the faster it recedes from us. If this isn't clear, here's a simple example. When stretching a child's toy spring, each coil moves away from its neighbor by only the width of a finger, yet two coils at opposite ends of the spring move apart by more than a meter. Now imagine the spring is infinite. The same applies to galaxies in the universe. Thanks to this mechanism, distant galaxies can recede from us at the speed of light, or even faster, because as a reminder, no prohibitions apply to the speed of space expansion, and it is precisely the expansion of space that is the reason why, at a certain distance from us, objects begin to appear larger the farther away they are. This occurs for the same reason we can observe objects that are currently receding from us at superluminal speeds due to the expansion of space. At the time when these, in quotes, superluminal objects emitted their light, they were much closer and occupied more space in the sky because the universe itself was denser. Despite being much farther now, the snapshot they sent us traveled all this time, and because the universe's expansion rate slowed for a period, as you recall, this snapshot has now reached us, showing a ghostly image of a much closer and much more ancient object. Thus, the farther back in time we look, the more compact a universe we observe. Therefore, a galaxy that is now farther than another galaxy might have been closer at the moment it emitted light. Hence, the paradox of perception arises. You have probably been waiting. Here's a real example. One of the most distant galaxies we have ever observed is GNZ 11. The ghostly snapshot we see traveled to us for approximately 13.5 billion years. So it seems to us that GNZ 11 is much closer, but it is not. Looking at GNZ 11, we are, in a way, looking not at today's universe, but at the universe as it was just 400 million years after the Big Bang. Let me remind you, it was much more compact then. Meanwhile, due to the expansion of the universe, GNZ 11 is currently about 32 billion light-years away from us, and it actually appears twice as large as a galaxy of the same size that is twice as close. A paradox of perception. You know that a light-year is the distance light travels in a year, and it would seem that since the universe is 13.8 billion years old since the Big Bang, we should be able to see a maximum of 13.8 billion light-years. But in reality, due to dark energy, we see much farther, which is also no secret to many of you. Today, the farthest distance we can see is a sphere with a radius of 46 billion light-years. And this is only for now. In the future, this sphere will continue to grow due to the expansion of space, but only up to a certain limit. By performing some calculations, we can determine the future limit of visibility. It will be approximately 33% larger than the current one. namely 61 billion light years from us. But gradually, the image of galaxy GNZ 11 will dim and disappear forever, because as you understand, the light that this galaxy is emitting now will never reach us, unless of course the expansion slows down again, and at this moment galaxy GNZ 11 is receding from us at a speed of 687,000 kilometers per second, more than twice the speed of light. And this is sad, but even sadder is that it doesn't end with GNZ 11. Think about it. More than 96.7% of the galaxies we can observe today have already disappeared by the same principle. 98.6% of the galaxies we will ever observe have already disappeared. In other words, in the future, we are set to see a total of 4.7 trillion galaxies, and 4.634 trillion of them are already forever beyond our reach, even if we could travel towards them at the speed of light. And only about 66 billion galaxies are still accessible to us today, I emphasize, today, because this is a problem that will worsen over time. Right now, if we assume that each of the 66 billion galaxies has as many stars as the Milky Way, about 400 billion, this means that there are approximately 60,000 stars disappearing from our field of view with every passing second. This is about 50 million stars in the time you've been considering this information. We will still be able to see their former light for billions of years, but any new light they create from this very moment will never reach us again. We are no longer causally connected to these objects. Regardless of what we do from this moment on, we will never be able to influence them, nor will they be able to influence us. Any information about these places is now fundamentally inaccessible to us. Even with arbitrarily advanced technologies, more than 98% of all galaxies we will ever see are already beyond our reach. If the force of space expansion can never overcome the gravitational force within galaxies, then gradually each galaxy or local group of galaxies will slowly sink into darkness, left in complete solitude. Gradually existing stars will burn out, particles will decay, black holes will evaporate thanks to Hawking radiation, and the universe will become merely empty space containing only dark energy, ensuring exponential expansion for eternity. Here it should be noted that dark energy is a kind of opposite to gravity. That is, the more filled space is, the stronger the force of gravity, and the emptier space is, the stronger dark energy becomes because, although it is counterintuitive, its density per square meter does not decrease with the expansion of space. So do you understand what is happening? As the process of the universe's expansion accelerates, there will be more and more empty space, which in turn will lead to an acceleration of the expansion process, which will lead to an increase in empty space, and so on ad infinitum. Events in some parts of the universe will not be able to influence events in others. Eventually, the universe will be empty space with only dark energy ensuring its exponential expansion. This is called de Sitter space, and according to physicists, it evolves much like the very early cosmos during the inflationary stage. But unlike inflation, this expansion will last forever. Can such infinite expansion be considered the end of the universe? The question here is what we call the universe and what end means. You see, if we consider, for example, the concept of time, it turns out to be one of the unresolved mysteries of physics. No one knows why it should flow in a particular direction. Consider particles in motion. Are they moving into the future or into the past? You don't know the answer because regardless of which way an animation of them might play, the laws by which these particles move would remain the same. It is believed that physical processes at the microscopic level are either completely or mostly symmetrical in time. If the direction of time were reversed, changing the direction of time in the equations would not affect the result in any way. The theoretical statements describing them would remain true. Now observe something else. Is paint separating from water or mixing with it? Here you definitely know where the past is and where the future is, because at the macroscopic level, there's an obvious direction of time. Thus it seems the only part of physics that cares about the direction of time is entropy. Why does your closet full of clothes become a complete mess again sometime after cleaning? Imagine your closet, and imagine all the possible ways to arrange things in it neatly. Excellent. Now imagine all the possible ways to arrange them messily. And because there are many, many more messy arrangements, the probability that the system called closet with clothes will gradually become more and more chaotic is higher than the probability that this system will continue to maintain some ordered form, because of the second law of thermodynamics, which states that in an isolated system, the total entropy cannot decrease. Your closet sooner or later returns to a state of disarray. You might say, well, I folded the clothes, thereby reducing the entropy inside the closet. Did I violate the laws of physics? No. Because the closet is not an isolated system, and you expended a lot of energy cleaning up. You digested food and exhaled carbon dioxide. The air in the room heated up through convection and sweat, so the total entropy increased even more. By the way, this is precisely why if you want to cool a room by leaving the refrigerator door open, the room will eventually not cool down, but heat up. And I remember being puzzled when it was said that air conditioners contribute to global warming. Every attempt we make to order some part of the world creates disorder in another part, usually in the form of heat. And we certainly don't know this for sure yet, but perhaps it is entropy that creates what we call time. Everything you see now, galaxies, stars, people, is all the result of the fact that, for some reason, the universe at the moment of the Big Bang was in an improbably ordered state, and the gradual movement from that initially ordered state of the universe to a disordered state is what we call the passage of time, like mixing paint in water. And just as we could not determine which way time flows in frames of paint already completely mixed in water, in exactly the same way, in a universe that has reached maximum entropy, the concept of the arrow of time ceases to exist. The fact that you feel the arrow of time is directed in one and the same direction, in other words, that very flow of time, indicates that the universe has not yet reached the equilibrium state towards which it strives according to the law of entropy. But having reached the de Sitter state, the universe will have maximum entropy, because from that moment on, the total entropy of the universe can no longer increase. This means that nothing more can happen in the usual sense, because for something to happen, energy must move from one place to another. But alas, the paint in the water has completely mixed. Yes, in a sense, a synonym for the word entropy is homogeneity. Given that the universe expands not from a single point but at all points simultaneously, when it reaches the stage of exponential expansion around any point, a sphere can be drawn, beyond the boundary of which will be a forever hidden part of the cosmos, just as those stars I spoke of are now forever hidden from us. And this has a name, the heat death of the universe. You might ask, what does this have to do with us? Why did I say this is worse than the demise of humanity? By the time of the heat death, we will have been gone for so long that it makes no difference. And here we come to what was mentioned at the beginning, because there is one nuance that changes everything. Ask yourself two questions. First, what happens when you have an infinite amount of time? And second, what happens when you have an infinite amount of space? The answer to both these questions is everything, literally everything within the laws of physics. Could I suffocate because all the oxygen in my room gathers in that far corner? Never. Entropy protects me from this situation because, as you remember, there are many more disordered states than ordered ones. Therefore, such a version of my demise would not even cross an investigator's mind. But in reality, when we say the word never, we often mean usually. A decrease in disorder in a system is possible. It is just extremely, unimaginably improbable. Usually people do not suffocate because all the oxygen gathers in one corner of a room. But hypothetically, if I were to sit here for an infinite amount of time, it would happen with 100% probability. With 100% probability. And a completely empty universe only seems empty at first glance. Because even where there are no particles, quantum fields still exist, and they never behave absolutely quietly. Quantum fields do not maintain a constant value. Their value at any point in space is always slightly jittering. These jitters are called quantum fluctuations, and they are nothing other than consequences of Heisenberg's famous uncertainty principle. And at the quantum level, or even on larger scales if you are prepared to wait long enough. And by long, I mean very long, truly strange things happen from time to time, caused by unpredictable fluctuations capable of shifting some part of the system into a state of lower entropy, lower homogeneity. Therefore, even if we believe that the universe had a beginning and that it is not infinite in space, nevertheless, in an expanding universe, time and space become so vast that extremely, extremely improbable events can and will occur with 100% probability. It is improbable that a whole piano would spontaneously assemble in empty space. However, physicists Anthony Aguirre, Sean Carroll, and Matthew Johnson calculated that if you wait for a period of time a trillion times greater than the age of the universe, you will see it appear right before your eyes. The less probable an event, the longer you will have to wait. But if you have infinite space or infinite time, and especially if you have both, then any arbitrarily improbable events will occur an infinite number of times. The consequence we can derive from the hypothesis of the heat death of the universe is capable of horrifying, no, paralyzing anyone who seriously contemplates it. Yes, the thought that pierced Nietzsche, which I mentioned at the beginning, a few months after his epiphany, Nietzsche would write the book The Gay Science, where he very cautiously touches upon his idea at the very end, in the penultimate passage of the first edition of the book, which he would call The Greatest Weight. It reads as follows. What if some day or night a demon were to steal after you into your loneliest loneliness and say to you, this life as you now live it and have lived it, you will have to live once more and innumerable times more, and there will be nothing new in it. But every pain and every joy and every thought and sigh and everything unutterably small or great in your life will have to return to you, all in the same succession and sequence, even this spider and this moonlight between the trees, and even this moment and I myself. The eternal hourglass of existence is turned upside down again, and you with it, speck of dust. Would you not throw yourself down and gnash your teeth and curse the demon who spoke thus? Or have you once experienced a tremendous moment when you would have answered him, "You are a god, and never have I heard anything more divine"? If this thought gained possession of you, it would change you as you are, or perhaps crush you. The question in each and every thing, do you desire this once more and innumerable times more, would lie upon your actions as the greatest weight. Or how well disposed would you have to become to yourself and to life, to crave nothing more fervently than this ultimate eternal confirmation and seal. The last passage of this book was titled Incipit Tragoedia, the beginning of tragedy, and this same passage would become the preface to the main work of Nietzsche's life. Thus Spoke Zarathustra, a book for all and none. The central idea of Thus Spoke Zarathustra was intended to be eternal return. The concept of eternal return asserts that time repeats in an infinite cycle, and that the same events will continue to happen in exactly the same way, over and over again, for eternity. In formulating this concept, Nietzsche most likely proceeded from the following premises. If the universe has infinite time, and the amount of matter in it is fixed, then sooner or later any combinations of this matter will be exactly repeated. Even if Nietzsche was far from today's cosmological theories, his conclusion may turn out to be precisely correct. Because this very conclusion is physically possible based on the hypothesis of de Sitter equilibrium, proposed by cosmologist Andreas Albrecht. The main idea of this equilibrium version of de Sitter space is that the origin of our universe and everything that happens in it can be seen as the result of random fluctuations in an eternally expanding space containing only dark energy. At some point in this space, due to quantum processes, a jump to a very low entropy state occurs and a universe arises, which then gradually returns to its normal high entropy state, once again becoming a de Sitter universe. Just like that oxygen, were it to gather in one corner, would gradually redistribute itself evenly throughout the room, and everything repeats over and over in a circle for an entire eternity. Of course, no one says that in every specific Big Bang, the history of that universe will repeat the history of our universe one to one. But this is the horror of infinity. Given infinite time, sooner or later our exact universe will be repeated with any desired precision, and we will be here again, communicating with each other, and this will happen an infinite number of times. And furthermore, given infinite de Sitter space, Big Bangs evolving exactly into our universe occur at every moment an infinite number of times. This entire process is described by a model of the universe called eternal inflation. I apologize for digressing so much, but we all speak so dismissively and casually about eternity or infinity without truly pausing for a second to consider what actually lies behind these concepts. You might say, again, what does this have to do with us? No matter how many times the universe repeats, it will no longer be us. But here the question arises, what does it mean to be you? One often hears from people who consider themselves non-religious that life is one and that we live only once. But isn't there more religiosity in this assertion than in the opposite? In other words, these people are saying that their consciousness is fundamentally impossible to recreate. A strong statement, because if you break it down into its premises, it turns out that consciousness is something detached from the material world. How much time is needed for a new Big Bang? Well, there are some calculations suggesting that inflation will generate a new Big Bang in approximately 10 to the power of 10 to the power of 10 to the power of 56. It towards this years. And you know what? If an entire universe can arise from a vacuum due to quantum fluctuations, then an individual galaxy can do so with much greater probability, as it is less complex and requires less matter for its creation. And if we continue to follow this logic, then the emergence of a single solar system is more probable. Or no, a single planet, or even just today, this very moment, and all other moments of your life. But wait, in fact, the appearance of a separate thinking structure is even more probable. For example, a human brain that contains all your memories and imagines that it lives in a vast and complex world and is currently perceiving information, perhaps through a narrative exploring hypotheses that are likely unverifiable. You do not notice this illusion because for you, as an observer, there is no space and time beyond your consciousness. That is, you cannot be an observer of a dreamless sleep. You fall asleep and immediately wake up to a new day. If a suspicion has crept into your mind that this is some kind of schizophasia, then in fact, more than one generation of scientists has puzzled over similar ideas. The idea of the spontaneous appearance of a brain in the void is called a Boltzmann brain, and this concept gained new relevance around the year 2002, when some cosmologists began to worry that in many theories about the universe, a human brain arises much more often as a result of random fluctuations than the emergence of an entire universe in which evolution would then occur, resulting in the appearance of humans. Simply because the emergence of an individual brain from fluctuations is, I repeat, much, much more probable. If a new universe, as you recall, appears once every 10 to the power of 10 to the power of 10 to the power of 56 years, then a Boltzmann brain arises merely once every 10 to the power of 10 to the power of 50 years. This leads to the statistical likelihood that people are mistaken in their memories of the past, and are actually unfortunate Boltzmann brains, endlessly appearing in an empty universe and doomed to almost instantaneous destruction. And of course, we do not know all the variants of self-aware entities that are not forbidden by the laws of physics and which, accordingly, our universe is capable of generating. Boltzmann brains are child's play compared to what the universe is capable of generating in the model of eternal inflation. But I will not continue to provide examples, and I do not recommend that you do either. Even if you or I are not Boltzmann brains, such ideas still attract attention. Looking at the insane number of parameters that had to align for the human mind to appear, as discussed in the context of why Earth might seem to break the symmetry of the universe, one cannot help but wonder if infinite time or space is involved here. The idea of the possibility of fluctuation so strongly contradicts our notions of a rationally ordered cosmos that leading contemporary cosmologist Sean Carroll called it cognitively unstable. The point is not that it cannot be true, but that if it is, then in that case, we might as well abandon any attempts to understand the universe, because nothing makes sense. And Nietzsche is often called a nihilistic philosopher, supposedly denying life in his philosophy, but this is simply the most obtuse thing one could possibly say about Nietzsche's philosophy. If the doctrine of eternal return entails the meaninglessness of what happens, then the doctrine of the Overman, formulated in the same, "Thus spoke Zarathustra," should become a kind of demand addressed to the human will, so that such meaning might exist. The ruthless idea of eternal return excludes all hope for a heavenly life and any consolation. But Nietzsche believed that it is precisely the Overman who has the courage to say a loud and confident yes even to such a world, leaving behind all the illusory hopes with which religion, science, and philosophy have hitherto consoled. By the way, if you want to read some fiction about the Overman, then perhaps the closest I know would be Theodore Dreiser's Trilogy of Desire. At the end of the third book, eternal return is even mentioned. Unfortunately, Nietzsche himself was not an Overman and called himself a decadent. For Nietzsche, who had a tragic destiny filled with pain and suffering, the idea of eternal return was devastating, paralyzing, and absolutely terrible. In his notes, he wrote, "I do not want to start life anew. Where would I find the strength to endure it?" In creating the Overman and directing his gaze towards him, hearing him say yes to life, I, alas, myself, tried to say yes. Perhaps that is why Nietzsche refers to his deepest idea only in one passage from The Gay Science, in two passages from Thus Spoke Zarathustra, once in Ecce Homo, and once in The Will to Power, as if not daring to look this idea in the face for long. 8 years after the Epiphany and the most fruitful period of his life, Nietzsche went mad. There are different versions as to why this happened, including drugs for insomnia, heredity, schizophrenia, and so on, but there is no consensus on this issue yet. Some even genuinely believe that Nietzsche's madness had a psychogenic origin. Be that as it may, the illness did not leave the philosopher for a step, and on August 25, 1900, Nietzsche died in complete madness. And fortunately for him and for all non-Overmen, the heat death of the universe is only one of 5 possible versions described in the book The End of Everything by Catherine Mack, which largely informed this discussion, and not every scenario implies the hypothetical possibility of eternal return. Author Catherine Mack is a specialist in theoretical astrophysics, and her book is a fascinating read on these topics. Theoretical physicist Freeman Dyson, known to the general public for the Dyson sphere, in his article Time Without End, Physics and Biology in an Open Universe, sharply criticized the physics community for neglecting the topic of the end of the universe. Implying a lack of serious work on this subject, he wrote, "The study of the distant future today seems as questionable an occupation as the study of the distant past seemed 30 years ago. If the analysis of the distant future raises questions related to the ultimate meaning and purpose of life, let us explore them boldly and without embarrassment. However, based on what we have heard today, perhaps it is not worth doing so. But again, it is important to consider that much of what has been presented are reasoned hypotheses that may or may not be confirmed. These remain profound questions